call today to learn about the suitability of instruments. My name is Jason Tilges from Transcat, and I'll be your moderator today. With me on the call is Howard Zion, Transcat's Director of Service Application Engineering. Before joining Transcat, Howard held positions at the United States Air Force Strategic Air Command, Lockheed Martin, NASA Kennedy Space Center, and Philips Electronics. During his 27 years in metrology, Howard has collected a wealth of knowledge. He has authored white papers, participates on NCSLI committees, and holds an advisory board position at the University of North Carolina. Howard is a valuable asset here at Transcat, and we're extremely lucky to be able to rely on his expertise for occasions like this. The presentation today will discuss the process of selecting instruments that are suitable for the measurement on your products or in your manufacturing processes. Today we'll spend the first part of our time in presentation, and we will end the call answering your questions. During any time, you can send questions through the question box to the right in your webinar controls. I also want to mention that this webinar is being recorded. Each of you will receive a follow-up email with a link to the recorded webinar and the slides of today's presentation. Okay, at this time I'm going to turn it over to Howard.
Thank you, Jason. Good afternoon, and thank you for joining us. I appreciate your valuable time in going through this webinar with us. I've got a lot of material to cover, so I'm going to jump right into it. Hopefully we'll have plenty of time afterwards for questions. If not, we'll follow up with questions offline afterwards. So I'm going to start with talking about the Takata airbag fatalities and injuries, and starting with a woman here who had injury to her eye from shrapnel from the airbag that went off in her 2002 Civic. And the fact that this product caused these problems and tracing back what the root causes were for this product to fail. So according to the records that I've been able to look up, the airbag malfunctions were due to 3 different reasons. Age of the airbags was one of them. Exposure to humidity was another problem that it caused, which led them to first look at states in the U.S., mostly in the southern states where high humidity was a problem, or where the humidity is higher that could cause this problem, as the first pass, and then looking at all other states after that. And the third was a statement from their Senior Vice President of Global Quality Assurance stating that potential production issues which we have worked to identify and address. So I want to take a look at each of those and provide like a translation of what that means, my translation. So the airbag, use of the airbags, or the age of the airbags, effectively is stating that the product has a shelf life and must be replaced after a safe usage period has expired. Now, the other thing they can do is a design change of the product materials in order to achieve a longer safe usage period or a more acceptable safe usage period. The exposure to humidity translates to higher humidity causes the explosive that's used to inflate the airbag to deteriorate. That causes the inflator housing to skive out of its holder and into the passenger compartment. Then pieces of the broken housing act as shrapnel, which is propelled into the passengers. The investigation is focusing on those explosive inflators and how well or how poorly they're sealed. And is that due to bad materials that could not maintain the seal? Was it possibly the testing on those seals that was providing a false acceptance and increases measurement risk, which resulted in the poor seal? And then the third statement, potential production issues which have worked to identify and address. It's a pretty vague answer, which indicates a lack of process controls and doesn't really pinpoint the problem. It could be, surmising what that might mean, it could be that it's inferior product or component designed by Takata or its suppliers. a selection of faulty materials used in the manufacture of the product. It could be false test acceptance of the product or the components of the product. In the end, all of these end in higher consumer risk, and all are traced to suitability errors of one sort or another. So I want to step now to discussing what is suitability. And following on the fact that this is an automotive product, I took a look at ISO TS 16949 for their quality management system for automotive suppliers. And in there I find in section 7.5.1 that item C is talking about the need for the use of suitable equipment in the process. D&E also connects with that by saying that you must have the availability and use of monitoring and measuring devices and implementation of monitoring and measurement in the process of manufacturing for automotive parts. So it doesn't really define what suitability there is. It just says that you must have suitable equipment. Taking a look at another critical area, medical device manufacturing. 21 CFR 820.72 states that equipment must be suitable for its intended purpose and capable of producing valid results. So again, this is the right context of suitability, but it doesn't define what suitability is. So what we're going to do through this webinar is discuss the details of how to determine suitability of instrumentation for the intended purpose for the application. We'll use a couple of examples to do that. So let's start with a very simplistic example of daily chores that you might do around the house. You have a nail that you're driving into a board, and what is the most suitable tool for the job? A screwdriver, a wrench, or a hammer? And more importantly, the question might be, which one have you never used to drive the nail? I'd be willing to bet everyone has, or a lot of people in the audience have used, other than the hammer, a different tool to drive that particular nail. And I'll admit that I've done the same thing. So if you said the hammer is the right tool for the job, then I'd ask, really? You'd use a hammer to drive a screw? All right, so I played a little trickery with the pictures. I changed it to a screw, but the concept is using the right tool for the job. And it's not just suitability of using the right tool for the job, but using it the correct way. So the learning objectives for this webinar are to understand the components of suitability of instruments, formulate your own definition of suitability, and then compare that to your organization's definition, and create a definition if your organization doesn't have one, which it may not have. Or if it does have one, perhaps enhance the definition you have for suitability of instrumentation, selecting the right tool for the job. So what are the reasons people use the wrong tool for the job in the first place? Well, typically from my own experience, it may be inconvenient to go get the right tool. I've got a screwdriver in my hand because I'm putting screws in a certain place, and I need to hammer in a nail that I see is loose, or I have a nail that I need to put in somewhere else. And it's a small nail. It's easy to drive into a wall putting up a picture or something. So I'll just turn the screwdriver around and tap it in. That may not be a problem for something simple like that. But it could also be because you don't know how to use the right tool or the right instrument for the job. Or maybe you don't own the right tool or instrument for the job. And then lastly, it could be that you can't afford the right tool for the job. When you think about other applications other than these simple ones, in some of the more complex manufacturing processes, it could be that you don't have the budget for the right tool to do the job correctly. So you use what you have. So moving to the complex process, it's easy to see that if people use the wrong tool for the job in a simplistic application, or the right tool but used in the wrong way, then for a more complex process, can you imagine how that might lead to errors? When you take a look at instrumentation and all the different types of instrumentation that are used to measure pressure or temperature, force, torque, voltage, current, there's a myriad of measurements that need to be made. And if you're not using the tool correctly, or if you're using the incorrect tool for the job, that can lead to incorrect results. So let's talk about measurement quality assurance for a second. Metrological traceability is important, but it doesn't mean anything in industrial processes if you don't maintain good measurement quality assurance program. Measurement quality assurance is more than just the instrumentation you're using. It's how you use it. And it's critical to the industrial manufacturing processes that are used to manufacture products in everyday life in order to keep product costs down, in order to maintain safety for employees and the consumers who use the products, to keep your product lead times from being delayed. And in the end, we have this calibration traceability chain that has a lot of expense to it, all the way from the National Measurement Institutes around the world to the secondary labs and calibration labs that are used to calibrate product lines. All of that cost is a waste if, in the end, the instrument isn't used right or the wrong instrument's used for the job to get the job done. So this leads to the question, where does risk creep into the measurement processes in production? So I won't go through every one of these, but just use this as a reference in the future to say that there are more than just suitability of the intended instrument for the job that affects measurement quality assurance. For product acceptance, basis of your decision for the product, suitability of the intended purpose, instrument application, and so forth. Here we'll focus just on the suitability of instrumentation for the intended purpose. And in short, selecting the right tool for the job. There's these other components as well that also impact traceability of measurement and measurement quality assurance in the products and your decisions on products, whether they're good or bad. All of these apply to that. So we're going to use an example here, and I've used this one in the past, where you have a module transfer process between a space vehicle and the International Space Station. And there's heaters involved to prevent ice buildup in the transfer of the module and the spacesuits, specifically in the gloves and helmet camera. And we're going to focus on that. And the main battery pack that provides a 12.5 volt source with a tolerance of 1.5 volts. And so the helmet camera requires, the heater requires 12 volts plus or minus 1 volt. The glove heaters provide a resistance of 57.7 ohms plus or minus 2.9. And they have a voltage source of 9 volts plus or minus 0.5 volt. So don't get lost in those numbers there. What we're going to do is take a look at different instruments that could be used for these different measurements and have a logical sequence that determines suitability of the instrument for the job. So summing up, in step one, you would determine what are all the measurements that need to be made in the process. And here we're listing a couple of 3 different voltages and a resistance value. Okay, so step 2 would be to collect a list of instruments that you're considering to make those measurements. So here we're listing 4 different multimeters, or handheld multimeters, 1 benchtop multimeter, and a long-scale DMM. So then the next step is going to be to collect the specifications for each of those instruments for the measurements we're trying to make. All right, so for the handheld Centec model, the 20 volt range would cover those 3 voltage ranges we're checking, and the 200 ohm range would cover the resistance measurement we're trying to make. So far, so good on that one. The Fluke 87 was the second one in the list. It has a 60 volt range that will cover the 3 voltages we need to measure, and the 600 ohm range that will cover the 1 resistance range that needs to be measured. So it also is good for, so far, for the application, just from a parameter standpoint. Same with the 34401, the 10 volt and 100 volt ranges can be used, as well as the 100 ohm range for the measurements. And finally, the Agilent 3458, which is a long-scale DMM, has a 10 volt and 100 volt range that can be used for the voltage measurements, and 100 ohm range for the 57.7 ohm resistance measurement. So those 4 instruments that we're considering cover the parameters that we need to measure. All right, so then the next step is to evaluate not just the ranges, but the accuracy and resolution of the instruments. So then, using the example of the Centec 37772 and measuring the 12.5 volt signal on the 20 volt range of that instrument, the accuracy statement from the manufacturer says that 20 volt range has an accuracy of 0.5% of the reading plus 1 digit. And we know also that the resolution on that range is 10 millivolts. So taking that accuracy statement and converting it to a tolerance using the 12.5 volt measurement that we'd be making, multiplying the 0.5% times 12.5 volts and adding 1 digit of resolution, which is 10 millivolts, comes out to 0.0725 volts. And now rounding that to the resolution of the instrument at 10 millivolts would give us plus or minus 0.07 volts. That's what the manufacturer states the instrument can perform to for that particular range and that particular voltage. All right, so now I've created a table here for each of the 4 instruments and each of the voltage measurements, as well as a table for the resistance measurements, and I've done that. That process we just went through of converting the accuracy statement to a tolerance in the unit of measure. And so it looks like a lot of information, but it's a relatively quick and simple thing to do. And here we show that first example of plus or minus 0.07 volts, again rounded to the resolution of the instrument at that range. And we've done that for every other reading as well. All right, so the next thing to do is, and this may be a new term to some of you, this is a Transcat term that we've come up with to reference another term that has been used in metrology world anyway. And that term is the test accuracy ratio, which we've converted now to a process accuracy ratio, to focus on that measurement that's used in a production or testing process. All right, so the process accuracy ratio is a calculation that takes the upper limit of the process minus the lower limit of the process, and I'll show you where those come from, and divides that by the upper limit of the instrument minus the lower limit of the instrument. So here we'll go to the 12.5 volts measurement. I'm sorry, we'll go to the 57.7 ohm measurement. And when we go back to the statement of the process that we're measuring, we said that the glove heaters have a resistance of 57.7 ohms, and the tolerance is plus or minus 2.9 ohms. So that's the process tolerance right there. In the case of the voltage measurements, you see the tolerance of 1.5 volts or 1 volt for each of those measurements there. That's the process tolerance for each of those measurements. So in the process accuracy ratio, we're going to take that 2.9 ohms, and mathematically it comes out to the plus 2.9 minus the negative 2.9 in the numerator for the process. And we're going to divide that by the instrument's accuracy, which for resistance is calculated to be plus or minus 0.8 ohms. So if you look at the table there, the Centec 37772, or the 57.7 ohm measurement, took the manufacturer's accuracy statement and converted it to a tolerance in the unit of engineering, which is in ohms, and that's how we got the denominator. All right, so we take the process tolerance in the numerator, the instrument tolerance in the denominator, and we come out with a ratio of 3.6 to 1. So that's another step in the process. We've confirmed so far that the parameters can be measured with each of the instruments, and now we're looking at our process accuracy ratio to determine whether that instrument is accurate enough to make the measurement of the process. The reason we want to look at an accuracy ratio is to determine whether that tolerance of the instrument is too wide or too close to the tolerance of the process that we're measuring. So it needs to have a healthy ratio. What determines the healthy ratio? Well, that really is the decision of the manufacturer of that component to say what that healthy ratio is. But for most applications, a 4-to-1 ratio is typically what you're looking for, or better. So you repeat that process accuracy ratio or PAR calculation for each of the different measurements, each of the different process tolerances versus each of the instruments you're considering, and you come up with those ratios. And you can see from this chart, and when you look at the Agilent 3458, these are almost 10,000 to 1, 7,000 to 1, 2,500 to 1. They're very, very large. And so that's definitely overkill for that measurement. It'll make the measurement, no doubt. When you get to the other end of the scale, when you're looking at the Centec model, you have a 21.4-to-1 ratio, 14.3 to 1, 8.3, and then this 3.6 to 1 that we calculated for resistance. So that one's below 4 to 1, and that may be a concern, or maybe not. Depends on the application and how much risk you want to take. And now, in the rest of this webinar, I'll be defining how much risk is too much risk. So another thing to consider once you've gotten all those process accuracy ratios figured out, and you're trying to determine which instrument to use, another factor you might pull into play is what are the other applications that instrument might be used for in other places in the production plant. If it's going to be used somewhere else, then you've also got to do that same process for where that's going to be used. Or if you're thinking about down the road where an instrument might be used, you might want something that's a little more robust in that PAR calculation so that you don't run into low accuracy ratios down the line. And then finally, the cost factor comes into play. So here we have each of the instruments we're considering. We can see that with the Centec 37772, it's a very low-cost item, it's 20 bucks. There is one PAR that's at less than 4 to 1, and the others are greater than 8 to 1. So that needs to be considered whether that's going to be a risk down the road or if that can be used universally. The Fluke 87.5 is a $400 instrument, but it has very good tolerances on it and gives process accuracy ratios of better than 9 to 1 across the board. The Agilent 34401, which is shown in the picture to the right, is a $1,000 instrument roughly, and all of its process accuracy ratios for this application are better than 300 to 1. So now the question is, if you want to spend 20 bucks, 400 bucks, 1,000, or $9,000 on the 3458, which are all better than 2,000 to 1. So clearly this last one doesn't make sense, and probably the 34401 is overkill for this application. So then it's down to the Centec and the Fluke 87. And do you want to spend 20 or 400? And so if you're thinking about other applications, especially for a handheld multimeter, you might want to go with the Fluke 87 because it's going to have tighter tolerances for its application and for its use in other applications in the production plant or in the field or for testing. But that's certainly something that should be taken into consideration in addition to this particular application, and does it meet what it needs for that application. So after you become comfortable with the PAR and you use that a little bit, that's a very simplistic way of getting ratios into place that say whether an instrument has too low of a ratio or way too high of a ratio, but whether it's acceptable or not. Then you want to take it a step further, because when you're looking at the accuracy of the instrument and you're taking a look at making those measurements in the process, there are other factors that come into play that can cause errors in the reading. And that could be operator training of the use of the instrument, especially for more complex instruments, gauge repeatability and reproducibility, variations that occur from one operator to another or with one operator alone. An example of gauge R&R might be a torque measurement, where different operators can induce different errors and cause different variations in the readings and cause that to be a false accept reading on the product. Also, the environment in which the instrument is being used. If you have a very sensitive instrument that requires tight controls on humidity or temperature or vibration or lighting, you've got to take that into consideration. And if you don't have those controls in place for the environment, does that throw the readings off? Does that give you a false indication? Storage conditions of the instrument when it's not in use can affect the accuracy of an instrument or the ability for it to make its correct measurements. And then, of course, how you handle the instrument during its use over its calibration interval, from the time, in between times that it's checked for its accuracy. All right, so an active measurement assurance program has to not only consider right tool for the job, but the regular calibration, and is that calibration performed correctly? Does it support the process where the instrument's used? Does it supply the correct, does the calibration include the correct tolerances of the instrument? Sometimes that can come into play as a factor. And the calibration has to be valid. In other words, the calibration measurement uncertainty has to support the measurements being made. And that's where we get back to that TAR, or what we call test uncertainty ratio, TUR. And whether those are healthy ratios as well between the instruments used to calibrate your instrument and making sure those are healthy ratios of 4 to 1 or better. So besides regular calibration, using the instrument or tool correctly, accounting for irregularities in the production measurement, process measurement uncertainties as opposed to just accuracy of the instrument being used, and then auto tolerance investigations, are those performed correctly? So even if you had this whole traceability chain that's done with healthy ratios all the way through, and your process accuracy ratio is healthy, if you find auto tolerances on the instruments that are being used in the production line are not being investigated properly, or if they're not being done at all, then you just really threw the whole traceability chain out the window. So that's a very important thing to consider. And then once you find an auto tolerance, is the corrective action being taken to make sure it's not impacting product. And that's really what the whole traceability chain is for, to get down to making sure that you didn't make the wrong decision about product being pass or fail, and that the instrument being used didn't impact that as well. So now I'm going to give you some more examples of how instrumentation measurements and incorrect readings can cause false accept or false reject in the production process. So let's say you're an engineer that needs to make a measurement of a solution used to treat the product. And the process is at 350 degrees Celsius, and that your acceptance tolerance of the process for that temperature being applied to the solution is within 2 degrees. Now you've got to figure out an instrument that's suitable for the measurement. Do you want to use an instrument with an accuracy that's equal to the process limits? So here we have 350 plus or minus 2 degrees, and that's what the solution has to be at. Otherwise, it doesn't treat the product correctly. You get some different results. And if you use an instrument that's the same accuracy, then you have a 1-to-1 process accuracy ratio. And that's not good because the instrument can drift the full amount during the cal interval, and that directly impacts the previous measurements you made in the process. All right, so let's say you have an instrument, you calibrate the instrument today, and you adjust that instrument to nominal during the calibration, and then it's taken out to be used in this process measurement for the solution of the temperature of the solution. So on that same day, you know that the instrument being used to measure that temperature is correct. It doesn't have any error at 350 degrees C. So that process measurement is good, because if I went back and checked that instrument again right after I took the measurement, it's still going to be where it was. Unless I've dropped it or mishandled it somehow, the chances of it varying within that one-day window is very, very minimal. But you don't have the luxury of calibrating your instruments every single day, right? Usually they're on a 1-year interval or perhaps some other interval, but the majority of what we see from our clients is 1-year interval. So what if it's on its last day of use before it's going to be recalibrated? Again, using a 1-year interval as an example, today is the 364th day. It's going to be calibrated today or tomorrow. And where is that instrument today, that temperature instrument I'm using to measure the solution? Has it drifted? How's it been handled? How's it been stored over time? So I don't know where that is until it gets sent in for calibration again. But if I'm using it today, the last day of its calibration interval, to measure that solution, then what happens to that measurement? And then when I find out where that instrument is tomorrow after its calibration, how does that have an impact on the measurement I made? So today I make a measurement with that instrument on its last day of use. I see that that value is right at 350 degrees Celsius. And I call that measurement good. Then I send it in for calibration. And it's found that it's at its upper limit, and then it's adjusted back to nominal. So it's found at 350 degrees, and it's brought back down to 350. Now, that may not be a realistic example of an instrument over its cal interval to drift to its full tolerance, but let's just say in this example that it does, for sake of discussing what happens to the process measurements where the instrument had been used over its last cal interval. So the instrument is found in tolerance because it's not gone outside that limit. And the question is, now I've got to evaluate, even though that's not out of tolerance, did that measurement move all at once due to some abrupt change in the use of the temperature device, or did it do a little bit over time over that cal interval? And how does that impact the measurements of the process since the last time the temperature device was calibrated? So you have to assume that the instrument shift occurred immediately following the last calibration, even though likely it didn't, because you don't have any other supporting evidence to show that when it actually had shifted. And because you don't know when it shifted, you have to assume everything is in question. All right, so again, it's not found out of tolerance, but there's a drift there that's pretty significant, and you need to see if that had an impact. All right, so the process measurements that were taken on the day the instrument was previously calibrated were not actually at 350. Now they were at 348 because that instrument had drifted all the way to the right. Now it's going to be adjusted back. And if you went back to take that measurement on that same process, remember the last day you did the instrument was under calibration just before it was turned in. You thought you were at 350. Now you're really at 348. So that process measurement is still good, but it's right on the limit. What if some of the process readings in that 1-year interval were at 348 degrees? And now you found out that that instrument was reading high and it's adjusted back down. If you went back and were able to measure those process measurements, they would be less than 348 and they would be out of tolerance. But the intolerance calibration would not have flagged that situation as being at risk. So you could have some risk in your product, and process measurements for those particular measurements would be bad. So again, that whole scenario that I just went through was talking about using an instrument that has the same accuracy as the tolerance of the process. And that's another reason why you don't want to do that, because you get any drift in the instrument, you're going to have drift in where your measurements were for the process. And that could throw a lot of them out of tolerance, and you wouldn't even know it. So now let's select an instrument that has twice the accuracy of the process, or half the accuracy of the process tolerance. When it drifts now, you've got a little bit of room there. It would only be off half the process tolerance if it drifted the full tolerance of the instrument. And if we went 4 times as good for the instrument being used to measure the process, that would be a 4-to-1 process accuracy ratio. And this is why typically most companies go with a 4-to-1 decision. If you get towards a 10-to-1 or greater, then it gets to be pretty expensive for the standards. And you saw that from the example of the 4 instruments used for measuring that previous process. Your price of the instrument and maintaining it goes up. And so there's some optimal level there where you're keeping this risk of bad process measurements to a minimum, but not increasing your cost greatly. So 4-to-1 ratio is usually used, and if it drifts to its limit for the instrument being used, then you would only be 1/4 of your process tolerance that would be used up. And you're minimizing the number of bad process measurements by doing that. So again, if we took it to 10 times or 100 times better, there's limits of technology, there's increasing cost, and it gets to be too prohibitive to go too far with the concept. So traditionally, a 4-to-1 ratio is sufficient to reduce the probability of bad measurements, probability of out of tolerance on the instrument being used, and reduces the impact on the process. So if one or more of those process measurements in a 4-to-1 ratio was at the lower limit in this example, and we found the instrument to be at its upper tolerance when it was calibrated the next day, going back to those process measurements, those that were at the lower limit or within that region for that tolerance of the instrument would be considered to be bad measurements. Now, the instrument itself was found intolerant, and it wouldn't trigger a flag for you to go back and look at that. But you understand there are some process measurements that could be bad, and you'd have to go back and look at all of them to determine which ones it affected. That could be cumbersome and costly. So how do you build something in to prevent that without having to go back and look at everything? So even intolerance results can impact the process. All cal data would have to be reviewed against the process measurements to understand whether there was an intolerance indication that would require nonconformance review. Impact studies are expensive, consumes valuable resources and costs. It could be in the thousands of dollars for evaluation of that. Parts or products likely have already been released or shipped, and could require product recall. So that that's not a good solution to do it after the fact. And even if it's released, it might require rework. But you can reduce the risk by using the concept of guard bands to protect the process. So what is the guard band? Effectively, you determine a realistic tolerance for your process, however you came up with your process tolerances for manufacturing or testing. And you back those off by the tolerance of the instrument being applied for the measurements. That way, if it's out of tolerance by its full amount, which it's usually not, but if it is, you've got some safeguard there, or guard band, to keep you from having bad process measurements. And I've seen quite a few companies that have put this into play. So the result is, even if that instrument drifts, its error is not greater than the measurement process would allow for these upper and lower acceptance limits that are inside the upper and lower process limits. And that protects the measurement. So to summarize, for suitability of instruments, implement a good measurement assurance program that covers not just the selection of the right tool for the job, but using it correctly, storing it correctly, having the right environment, all of those things. So understand good suitability selection, going through the parameters and process accuracy ratios. Document that if you need to support why you selected the right instrument. And for replacement of that instrument in the future, you'd want to go through the same process. If you ever changed your process tolerances down the road for whatever reason, you'd want to go back and reevaluate the instruments that were selected for the job to make sure they're still suitable. Guard band the process tolerance limits to reduce your nonconformance reporting evaluations, and understand both the process and the calibration to ensure the intent of preserving good measurements on the product is not lost. When you find out of tolerance situations for your instrumentation, Be sure that you're doing out-of-tolerance investigations, non-conformance reporting investigations. And if you need help in how to do that correctly and have the correct forensic mindset to find the right root cause and get to the right solution, get help if you're in over your head. We're here to help, and we offer consulting services to help you with those reviews. Because in the end, running your business is not about just the rules that are in place and the policies and procedures. It's about making a safe product and making a profit. Measurement quality assurance should be designed to help you minimize those risks in determining whether your product is good or bad without having false accept or false reject situations with your product, particularly when it comes to safety. Suitability of instrument selection is a key part of guaranteeing these good measurements. Too often, measurement quality assurance is not fully implemented with all 10 of those categories. I didn't go through all of them, but again, those are all important parts of making sure your measurements aren't leading you down the wrong road to the wrong decision about product being good or bad. The last thing you want is to end up having a product that you believe is good, and it ends up hurting or killing people. So make sure that your measurement quality assurance program is robust and that it covers everything from suitability of instrumentation to the use and storage and handling of the instrumentation, to product selection and materials and all of those things that impact your product. So that's the end of the presentation. I'll turn it back over to Jason, and he'll close it up and take any questions that we can fit into the remaining time.
Great, thank you, Howard. That does conclude our presentation portion of the webinar. We had a lot of questions come in throughout the course of the webinar. Now, before we get into the Q&A, I would be remiss if I failed to mention that Transcat has a great deal of Cyber Week promotions currently underway at the brand new Transcat.com. In case you didn't know, we did launch a brand new website about 2 weeks ago, which will, by the way, include a ton of free white papers, webinars, videos, and other content from metrology and quality experts and thought leaders such as Howard. So please look for that content to start coming your way very soon. Currently, as it is the season, we've launched a huge Cyber Week promotion, as I said, with discounts on all kinds of products up to about 30% off. Fluke, Magyar, Agilent Keysight, Aditel, Hioki, Milwaukee Tools, and many of our other product lines are on sale. Now, I know many of you are probably on the metrology, quality engineering side of your company, not necessarily on the purchasing side of things looking for pricing, but if you or someone you know is in the market for new test and measurement instruments, please check out the new site. Think of us, call us. If you have any questions, visit us at transcat.com or contact Transcat at any time, 800-800-5001, or at sales@transcat.com. I appreciate you letting me get that plug in, and now we will move into the Q&A session. So just as a reminder, if you would like to ask a question, please send it through the question box on your webinar controls. And we did have a bunch of questions come in throughout the course of the presentation, so I will get into those shortly. All right, let's see. All right, the first question, Howard, is what are your rounding rules and basis for your rounding rules, i.e. why round tolerance of 0.725 to 0.7 instead of up to 0.8?
Yeah, so conventional rounding rules apply because the circuitry in an instrument is going to do the same thing. It's going to take that next digit that can't be seen and either round down or round up based on that value. 4 and under would round down, 5 and up would round up. And so since you can't see that last digit, there is that instrument repeatability or resolution uncertainty, and that usually is included as part of the measurement uncertainty for the calibration of the instrument. But you should also use that unseen digit as a factor in the PAR, converting the PAR to PUR, process accuracy ratio versus process uncertainty ratio. That gets into creating uncertainty budgets for the process, and that's a little more than what this particular webinar is intended for. But just to keep that short and succinct, typically a process uncertainty would include the accuracy of the instrument, which we did show in the presentation. It would include the uncertainty of the calibration of that instrument as another component. And then the third one will be a repeatability or resolution of the instrument as well. So 1 digit of resolution would be a third component. And then you would take that into account that way. But as far as rounding goes, typically it rounds up or down based on conventional mathematics.
Great, thank you. And we did have another attendee comment and say NIST has an excellent rounding SOP in case you need a reference there.
Appreciate that.
Okay, next question. If you do have guard bands in place and your measurement fails between those and the tolerance limits, is there any way to easily broaden the acceptance limits?
Well, if you're having, here's what I believe I understand that to mean. So you have, what I used in the example was hitting the very edge of the limit but not going out of tolerance. But of course, you'll have instruments that are out of tolerance, and it's not going to guard band against those. So then those would be susceptible measurements. And you have to go back and see if it impacted, if the values that the instrument resulted in impacted the measurements in the process. If you continually have repeated out of tolerances that are causing that review to have to be done, which is extensive and exhaustive, then you might consider that that instrument's not maintaining to its performance limits the manufacturer states it'll maintain. And you may have an issue with that particular model and need to replace it, or perhaps that's a warranty issue with that particular instrument, but I would say that it's probably an instrument problem for that particular model, and you might want to consider a different model, because that gets very costly for you to have to continue to repeat those evaluations time and again. So if you're having repeat out-of-tolerance situations, which I think was what the question addressed, certainly want to consider, is it the instrument that's a problem? Is it the operator using the instrument incorrectly? Now we're talking about the calibration of the instrument, so was the calibration done consistently over time? A lot of questions there as to why that out-of-tolerance continues to recur, because that should not be happening.
Okay, thank you. We had a question asking for you to restate or clarify what guard banding is. Is that something you want to potentially handle offline, or is that something you want to get into now?
Yeah, so just to repeat that, guard banding is, first of all, getting the right ratio for the process accuracy ratio, selecting the instrument that's a 4-to-1 or better, or whatever your company's procedures or quality procedures state that it should be. You may already have those in place that states that an instrument that's used for measurement has to be X number of times better than the process being measured. So whatever that ratio is, you should be following that. And to guard band would mean to take the tolerance of the instrument that it's allowed over its calibration interval and use that to subtract from the process tolerances you already have in place to create what we call an upper and lower acceptance limit, not a process limit, but an acceptance limit that's inside of those tolerances for the process. Hopefully that clarified that.
Okay, thank you, Howard. And we had a couple questions about sending a copy of the presentation. Yes, with every one of these webinars, we do send a link out to download a copy, a video recording, and the PowerPoint slides of the presentation, so you can always go back through those at your leisure. We should probably get those out tomorrow, but definitely by the end of the week. What else do we have here? Is there a recommended practice guide by the NCSLI for out-of-tolerance NCR evaluations?
Not to my knowledge, but Transcat has developed a training seminar on how to evaluate out-of-tolerance situations on the next level in the traceability chain. And so we're available for consulting or training for that.
Okay, thank you. Okay, looks like we had a question back during your PAR calculations. Is this the same as the 4-to-1 accuracy ratio required by Z540? Does that make sense, or should I ask for clarification?
So I assume that's Z540.3 and talking about less than 2% consumer risk. And that's really the concept that we're after, is making sure that all of the components are taken into consideration when you're making a measurement that include, like I said, the instrument accuracy, the uncertainty of the calibration of that instrument for those values, the resolution of the instrument, any operator error or variations that come from the operators of using the instrument for the process. All of those things taken into account really gives you a process uncertainty ratio, not just a process accuracy ratio. And it takes all of that into consideration to help reduce the risk in making a decision about a product that is good when it's really bad, or that it's bad when it's really good. And if I haven't fully answered these to your satisfaction, feel free to send the requests in to us, and we can give you a more full explanation or have a discussion.
Great, yes, and you can, like I said, we'll be sending out the copy of the presentation. You can respond directly to that email or contact us if you have our direct contact information, which some of you may. What else do we have here? Okay, I missed how you calculate the PUR, process uncertainty ratio. Is that something you can go back through, Howard?
Yeah, so again, distinctly separating PAR from PUR. PAR just uses the tolerance of the instrument in the denominator, and the PUR would include other factors that you put into an uncertainty budget, which I won't go into detail here, but that includes at a minimum the accuracy of the instrument, as we did with PAR, but also the uncertainty of the calibration of that instrument, the resolution or repeatability of that instrument, and any other factors that would be considered major factors in making a measurement. So PUR would consider all of those things combined together to give that denominator value.
Okay, thank you. Just a couple comments too. Critical measurements can benefit from a pre-post-cal in certain circumstances. We did this in the nuclear industry. I believe that was a comment from about the midway point of the presentation.
Okay. Pre and post-cal results? Is that what it was?
Critical measurements can benefit from a pre-post-cal in certain circumstances. We did this in the nuclear industry.
Yeah.
Okay. All right, we've got time for a couple more. If anybody has any other questions, please send them through. You showed 2 industry standards that address suitability. Are there other references available that can help me better understand this?
Yeah, what you want to look for in any of the industries that you work in is your source documents that give you guidance as to what performance your company has to have against national or international standards. And what you want to look for in there is what the requirements are for calibration, search on keywords like calibration, metrology, suitability, things like that, to see what it says about what your requirements are for selecting the right instrument for the job effectively. And so that's what I did in these other standards, is I looked for the term suitability. And every industry has its own guidance documents or requirements that it must adhere to. So I would suggest you pull that up and do a search on it, see if you can find anything related to that, or find the section related to calibration and what the requirements are.
Okay, great. And we had a question about RSS applications. I'm not sure if we got into that at all, or if that's something that you're familiar with.
Yeah, RSS is the root sum square. It's a mathematical computation to pretty much average out the effects of different values. So if I was going to combine, let's say I'm taking a measurement that has a couple of instruments that are used in the measurement process to get the final measurement. And I would have to somehow combine those 2 values to get the denominator tolerance for the PAR calculation. I would RSS those together, or do a root sum square of those values. I take each value of the tolerance that the manufacturer states for each of those instruments. I would square those values, I'd add them together, and then I'd take the square root of that. That would give me an RSS value for that denominator in the PAR calculation. Now, effectively, worst case would be that each of those instruments had drifted to their outside tolerance at the same time, which is unlikely, but if it did happen, that would be worst case, and that would be a straight sum of those tolerances for the denominator of the PAR. But more realistically, an RSS value would say, well, not likely both of those will be at this extreme values at the same time. And so we root sum square them to give a more realistic value. And that's what root sum square is used for. It also relates to NIST Technical Note 1297, Law of Propagation of Uncertainties, which comes out to an RSS calculation.
Great, thank you, Howard. That concludes our time for today. If you have any further questions or would like to find out more about Transcat's product and service offerings, please contact us at 800-800-5001 or the number on your screen, which is 800-828-1470. We're also available on the web at transcat.com, or you can also email us at sales@transcat.com. Thank you very much for joining us today, and we hope you found the information useful and applicable to your processes and jobs. Have a great week. Thank you, Howard.
Thank you.